My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 366. In this lecture, we will try to understand SGD algorithm, that is stochastic gradient descent algorithm. So, we have seen in our previous lecture that in linear regression, the gradient descent update function looks like this, isn't it? What is that function? Wj plus 1 equal to Wj minus r into sigma I equal to 1 to n minus 2xi into yi minus Wj transpose xi, isn't it? We have seen, since this summation, what is the summation? Sigma I equal to 1 to n. Since this summation has go through all the points, it must go through all the points when n is large. Just see, when n is large. When n is large. I will repeat. We have seen, since this summation has go through all the points when n is large, this takes lot of time. We say this is the problem with apply this is the problem when we apply gradient descent for data science applications, especially when the data is large. There is a very nice solution to this, which is called stochastic gradient descent algorithm. If I have to pick one algorithm which is the most important optimization algorithm in the whole of data science, I will pick SGD, stochastic gradient algorithm. SGD is literally the most important. I can say it is most important optimization algorithm. Most important optimization algorithm. Yes, the most important optimization algorithm in data science. By the way, in data science, we use lots of algorithms. There are many algorithms. The most important is SGD. Literally, it is becoming the cornerstone, the most important algorithm, the most important optimization algorithm is SGD. We saw gradient descent. We modify gradient descent slightly and make it SGD, stochastic gradient descent algorithm. In deep learning, people are modified SGD. Further, I will repeat, in deep learning, people are modified SGD further and come up with many variations like ADAM. Yes, these things I will discuss in future classes, ADAM and ADAGRAD. These all are variations of SGD, which are literally becomes the most important algorithm in data science today. SGD is as important as linear algebra to data science today. In this current modern world of data science, earlier it was not so much, but today it is literally the most fundamental thing. Having said that, let's see what is SGD. What is this? What is SGD? We will try to understand. This is Wj plus 1 is equal to Wj minus, what is this, r into sigma I equal to 1 to n minus 2xi into yi minus Wj transpose xi. It's the gradient descent, isn't it? What is SGD says? SGD says very intuitively, instead of using all the points, instead of using all these n points, instead of using sigma I equal to 1 to n, instead of using all the points, let's just say Wj plus 1 is equal to Wj minus r into sigma equal to 1 to this what it says, Wj plus 1 is equal to Wj minus r into sigma I equal to, instead of 1 to n, I must say, instead of I equal to 1 to k minus 2xi into yi minus Wj transpose xi, isn't it? What is this k? K is less than n. what we have done is we replaced n with k. Then what is this k? 1 less than or equal to 1 less than or equal to k less than or equal to n, isn't it? Instead of using all the points, pick a random set of k points. That is important. Pick a random set of k points. Just see this one, what it says here. What am I doing? Instead of I equal to 1 to n, I am writing k. Now what you have to do here? Pick a random set of k points, isn't it? K points. Remember, k can also be 1. K can also be 1. That's important. Or k can be n also. K can be n. Pick a random set of k points and do this update. And if you do this enough number of times, if you do this update function enough number of times, the solution that you get W star, ultimately what will you get? You will get W star, isn't it? The solution that you get W star with GD, with gradient descent, we know how to find W star, isn't it? Even you know how to find W star with W star with SGD. Let me say stochastic. Let me say like this. Yes, W star with GD means gradient descent is same as W star with SGD. They are of same, isn't it? Yes, remember, I will repeat. Remember, k can also be 1 or k can be n. K can also be 1, k can also be n. Pick a random set of k points. That is important. Pick a random set of k points. Random set of k points and do this update. Apply this update, isn't it? If you do this enough number of times, if you do this update enough number of times, the solution that you get W star with GD, W star is same as W star with SGD. Of course, there are some mathematical conditions under which this W star ZD is equal to W star SGD always true. Don't worry about deep mathematical proof of it. What it says, if you pick k points randomly from the total data set of n points, if you do the summation over k points such that k could be anything from 1 to n. Let's assume n equal to 1 million. Let it be n equal to 1 million. Isn't it? 1 million means what? It's 10 lakhs. Isn't it? 10 lakhs. Isn't it? Your k could be, it may be 1. Your k could be, it may be 100. Your k could be, or it may be even 10,000, or it may be 1 lakh. Isn't it? What is the condition? Your k must be lies in between 1 and that n, isn't it? Any number is all right. We will come to a special case here. For all it says, if you keep doing iteration, the solution that you will get with gradient descent is same as the solution that you will get with stochastic gradient descent. This is called stochastic because stochastic basically means probabilistic, or wherever you use randomization, here we are using random set of points and hence it is called stochastic gradient descent. Now your question could be, let's assume we are using gradient descent and let's assume I need 100 iterations. Let me compare like this. Otherwise, let me write like this. Yes, you are using gradient descent. Let me assume your n equal to 1 million points. 1 million points. How many iterations? 100. You need 100 iterations to converge X star. What does it mean? let's assume we are using gradient descent GD, and let's assume I need 100 iterations. Suppose I need 100 iterations to converge or to obtain X star using stochastic gradient descent, SGD. Let me say, using stochastic gradient descent. Suppose let's say my n equal to 1, isn't it? N can be 1. N equal to 1. Let me say suppose let's say n equal to it's in gradient descent it is 1 million, isn't it? Let me say in stochastic gradient, let it be n equal to, let me say 1000. Let n equal 1000, because I am using fewer and fewer data here, isn't it? Now in stochastic gradient descent, probably you reach what it is here. I must not say n here, I must say k, isn't it? In the case of stochastic gradient, I must say k, isn't it? K equal to 1000. In stochastic gradient descent, probably you reach X star, optimal solution. X star means in more than 100 iterations, to converge X star, isn't it? Let's assume we need how many iterations? Let's assume I need 500 iterations. 500 iterations. If you perform SGD, let me say with k equal to some 10, instead of 1000, let me assume k equal to 10. You probably require 1000 iterations. You probably require 1000 iterations to converge. 1000 iterations to converge X star, or to reach X star, I can say, isn't it? What is k here? K is number of random points. K is equal to number of random points. What is k? Number of random points that you pick in each iteration, for updating, isn't it? That is important, for each iteration for updating. Remember, the set of k points that you pick for first iteration will be different for set of k points, will be different for set of k points that you pick for second iteration. Isn't it? That you pick for second. You need to pick these random set of k points every time for every iteration. The one that you use for wj2, the one you use to update from wj to wj plus 1 and wj plus 1 to wj plus 2, we will use a different set of k points. That's important. Here we use one type of whichever k points we are using to update from wj to wj plus 1 need not be same as the set of k points which are using from wj plus 1 to wj plus 2. We will use different set of k points. That's very, very important. Don't use the same k points. You have to change the set of, random points at every update or at every iteration. So the interesting part here, k is often called as batch size. This is known as k is often called batch size. In stochastic, k is batch size in stochastic gradient, because you are taking batch of k random points. Oftentimes people just use k equal to 1. If you take k equal to 1 and it is called SG, k oftentimes just use k equal to 1 and call it SGD, and k, let's say, greater than 1, but of course significantly less than, and this is often called batch SGD, isn't it? K equal to 1 means people are calling it as SGD, and if it is k is I can say n is significantly greater than k is greater than 1 means this is known as batch SGD, isn't it? It's called batch SGD because you are using a batch of k points, where batch SGD, in the case of batch SGD, k is not equal to 1. Depending on the terminology, some people would call this is also as SGD. Some people, depending on this one, some people used to call this as SGD, and depending on some textbooks, isn't it? K may be 1, k may be in between 1 and n, isn't it? Depending on the context, instead of saying context, I can say depending on the textbooks, people used to write with different names. But in some textbooks or in some blogs, you will, or you can say k equal to 1, they call SGD when n greater than or equal to k greater than 1, batch SGD. People generally, they used to call this is SGD, this is batch SGD with batch size. If I say k equal to, let me say, for example, n equal to 1 million and k equal to, let me say, 100. Therefore, what can I say? Batch SGD with batch size 100. That's what they call it. SGD is very, very efficient. Think about computation. Instead of using all points, for example, if I say n equal to 1 million, instead of using million points, I can just maybe use 100 points at each iteration. But from one iteration to other iteration, the set of points should be changed. That is important. If I use these k points, in one first iteration, k points will be differ from second iteration k points. Second iteration k points will differ from third iteration, isn't it? The set of random points should change, and picking of random set of points is very, very easy and computationally. So SGD is, to reiterate, the point, SGD is most important optimization algorithm in whole of the data science. In modern data science, extremely important. It is very, very simple. It is basically adding randomness. This SGD adding randomness or stochasticity to pick up k points at a time, in every iteration. Very simple and very, very elegant algorithm. Just go through this, and if you have any difficulty, just keep a comment. Thank you very much.